just noticed that I say okay at the beginning of almost every video, so I'm not going to say that this time. We are continuing on with class 24. I'm recording right now. And we're going to talk about dimensionless parameters and similarity laws as they apply to pumps. And these are often called affinity laws. That sounds pretty impressive, the affinity laws. Okay, there you go. So for any pump situation, the following variables define the solution. And for whatever reason, that work dropped down there, right? So we have head, work, or efficiency. And so these are the dependent variables, right? So these are the ones that we want to find, that pump head. I think the A is for available. The shaft work and the efficiency. And so the dependent variables are some diameter, sometimes that's the impeller diameter usually, some characteristic length, the roughness inside the pump, the flow rate, which you can also think of as a variable that we'd want to determine. But here we're going to treat it as a dependent variable. The angular speed, right? So the rotational speed could be RPM, the viscosity, density, and gravity. So, these all describe what all those were. I didn't have to read them out. But anyway, you get the idea. So if you do a Buckingham pi on these main variables up here, the head, the power, and the efficiency, you've ended up finding that you have these dependent pi terms. I should say that actually before we get to that, before we go up to these main ones up above, here would be the dependent pi terms. And so the results of doing these main guys up above, the head, power, and efficiency, we have names for them, right? So we could have the head rise coefficient, which is this grouping right here. We could have the power coefficient, which is this grouping right here. And we could have efficiency, which we would just call efficiency. We don't have a name for it. And then lastly, we could have the flow coefficient, right? Well, that flow coefficient is actually in amongst the dependent terms. So with other similitude things that we covered, and so let's see what class did we cover similitude in? I think it was class 16. Right, so if you go back to class 16, we dealt with similitude. The big idea is that when doing a model and a real thing, if we take care of all these dependent terms, then we can go ahead and use this main term. Well, that remains true, but here quite often what we will do instead, if we have one pump of the same family, we could use the parameters from that pump to use another pump within that family and find out what a change to one of these parameters would be. Most often it's going to be impeller diameter or RPM, but it could be other aspects as well. So let's work through those. Pump scaling laws, for geometrically similar pumps, or they could be the same manufacturer, or it could be actually the same pump model, but just done at a different diameter, impeller, or speed. These are called a family of pumps. And so if this rule is true, and this is like the main rule, and we want to make sure that usually the fluid's going to be the same, right? So what we can, and that if that first rule is true right here, that the flow coefficient, then we could have this head coefficient would also be true. And then this power coefficient, and then the efficiencies, we can predict those will be equal to each other as well. So as I mentioned, for a given pump 1, we can evaluate another pump 2 with the following ratios, and there's a lot of ratios here. So if the diameters do not change, so if it's the same impeller diameter, then we could say the flows are directly proportional to the velocity, the RPM, angular speed of the pump. And the heads are proportional by the square of the angular velocities, and the power is proportional by the cubic of the angular velocities. Now, if the RPMs are the same, but we change the impeller diameter, we have this relationship, which is interesting, that the flow is proportional by the cube of the diameter. The head is proportional by the square. And then this is really weird that the power is proportional by the diameter raised to the fifth. But if you look back up at these equations up above, you can work out how that might be true. Before we go to an example or a couple of examples, we also want to take a look at this useful specific speed concept. And the specific speed concept can be used to select a pump, right? So if we have just a hypothetical pumping situation and we don't know what kind of pump to use yet, we could use this specific speed, which is not really dimensionless. And by the way, there's also one, because we commonly use RPM, gallons per minute, and head and feet. Here's one where this really isn't dimensionless, this specific speed. But we can find from a chart like this one below where we might want to, what type of impeller or type of pump we might want to use. So you can see as we go higher and higher in the specific speed, the an axial flow type of pump becomes more desirable. But as we go on a lower specific speed, we could see that we have this tall impeller that's more useful with a larger diameter, chances of having a better success. I think this is just more information here about, well, at least, no pun intended, more specifics here about, there's the specific speed and gallons per minute. Now, I guess this is all for the same gallons per minute. You can see the typical head that you could anticipate for that, and the different operating range for the RPM and the diameter of the impeller, and also what they're calling the eye, which is the diameter of the inlet. Another graph, and this might also be useful in trying to determine whether you wanted a centrifugal pump or an axial pump. You could kind of see some of the traits that they behave a little bit differently in terms of the horsepower versus capacity, or head versus flow rate capacity, or the efficiency. The efficiency doesn't really change all that much, although it does drop off at the higher end for the axial flow pump. And here's an example of an axial flow pump where we have it submerged. Interesting. All right. There's also something similar that we can do for the net positive suction head. So there's, I don't have the figures up here, but I think there's another figure where we can find, based on these relationships, we can look for a pump that's more suitable for the net positive suction head that we have, that we need to use. All right, so here is a centrifugal pump, provides a flow rate of 500 gallons per minute. And when operating at 1700 RPM against a 200-foot head, and we want to determine the flow rate and developed head if the pump speed is increased to 3,500 RPM. So I'll try to write onto this. I don't really like writing onto the PowerPoints, but sometimes let's see. And also I'm writing with the screen vertical. So what we'll use here, if we have the same, this is the same pump, right? So it's we're going to use the same diameter. So what we can say is we have a relationship between the flow rate, which I'm going to call Q, a lot of times I'll have that V dot with a cross out, but here we go. And by this I mean that 1 is the new pump, and 2 is the old or new pump speed. Sorry. And so 2 is the old pump speed. Could have chosen either one, doesn't matter. So what we end up saying is Q1 is going to be equal to omega 1 over omega 2 times Q2. And because these are all ratios, we don't have to take any units conversions. So just 3,500 divided by 1750. And just as you'd expect, it's just going to double the gallons per minute. So we get 1,000 gallons per minute. Boring. However, for the head, we're going to use HA1 over HA2. My handwriting is terrible when you're writing vertically. Omega 1 squared and omega 2 squared. And so HA1 is going to be 3,500 squared divided by 1750 squared times 200, because our head is 200 feet. And we get 800 feet. And then we could find the power. Okay, so now we need the old power, which was omega, let's call it 2. It's going to be H2 gamma. And then I guess I'll go Q2, even though I wrote it on my page differently. So we have 200 feet times 62.4 for this specific weight, and then times the flow rate of, oh, I need to convert this. So I'm going to go, the old was 500 gallons per minute. I need to divide by 7.48, divide by 60, and then I need to also divide by 550 to get it into horsepower. So that's going to be, I can't read my own handwriting, 25, what happened here? 25.28 horsepower HP. So if we use these affinity laws here, we have that we'll use that omega, not omega, W dot, or the power 1 over power 2 is going to be related by the cube of these. So power 1, trying not to call it omega for some reason, I keep wanting to call it omega, is going to be 3,500 cubed divided by 1750 cubed times 25.28, and what we end up with is 202.2 HP. All right, so here are the things that, well, I guess it's these guys that I wanted to, yeah. So we want to determine the pump's flow rate, head, and I went ahead and got the power. We could have just went and used the new head and the new flow rate and gotten that same power, by the way. But this is just to demonstrate that we could use for the affinity laws. And it kind of makes sense that if this is to the 1 and this is to the 2, that this would be to the 3, right? Because we have power is flow times RPM. Not RPM, flow. Well, no, we could say, well, head is, power is flow times head, right? And they're all related by the 1, 2, and then 3. I guess that's the word I wanted to say. Hopefully that's the word. I'm going to go a little longer here, just to include this last example and be done with it in one video. All right, so a certain pump is known to have a capacity of 3 cubic meters per second while operating at a speed of 60 radians per second against a head of 20 meters. Based on this information, and this is the figure that we have that I showed in a previous slide, would you recommend a radial, mixed flow, or axial flow pump? All right, so the equation, let's see if I can get this to work right there. I'm going to use, whoops, one more down, right there. I'm going to use this equation right here, and we're going to come back to this chart to try to pick it out, and I believe it's going to be this one right there. We're going to use off that. So this NS is equal to omega square root of Q divided by G times HA. Whoops, should be a bracket, to the 3/4. So if we do that, we have 60 radians per second, square root of 3 cubic meters per second, divided by 9.81, multiplied by 20 meters, and raised to the 3/4. You end up with 1.982, right? So that's the parameter that we want to look up in this right here. There we go. So I had 1.982. That's really close to the 2. So it looks like it's a mixed flow type of thing that has impeller shrouds that aren't nearly as large as this one over to the left. So looking through a pump manufacturer, we would go mixed flow. It's not exciting, but it gives you an idea of that we can find some parameter to use to make a design decision, which is something that's pretty common. I'd also point out to find out is this dimensionless? And the way I would go about this is I would say, okay, I'm going to write this out. First, I'll go by units instead of by dimensions. I guess I could go by dimensions. Sure, I'll go by dimensions, right? So we have time to the -1, right? And then we have a square root of cubic meters per second. So that's going to be a length in the cubic, but they're squared. And it's per second right there. So it's going to be time, but it's square rooted. So it's right here. Right, so it's on the denominator underneath there. Now we have to flip this. This is kind of a difficult one. So we have to pay close attention here. We're going to have meters per second squared, but it's on the denominator, but it's to the 3/4, right? So that's going to be a length minus 3/4, right? But now it's divided by the square. So instead of 3/4, it's going to be 3/2, and it's going to be positive, right? So am I going to do that? Yeah, so it's going to be time, and it's going to be to the 3/2, right? And then lastly, we're going to have a length that's to the 3/4, but it's underneath. Right there, right? So so to get this, they did a seriously Buckingham Pi thing to get this dimensionless parameter. But we could see, okay, so a -1, and we have a 3/2, a -1 and a -1/2, right? You combine those together, that'd be -3/2 halves, so that we get rid of those. Okay, cool. And then we have a 3 halves and a negative 3 halves, negative 3/4 and negative 3/4. Right? So those will cancel out. What's going on here? How come I didn't do that? Okay, there we go. So yes, that should have been a question mark. All right, so we're done with class 24. It's long videos. Don't think I'll be able to get to this topic in class 24, but maybe. Or at least I recorded a video for it.